Right now we'll be deriving Maxwell's relations from thermodynamics, and honestly, I have not like prepared for this thing, but I've just seen how this thing works on Wikipedia, and let's give it a try. So, essentially, the only thing that we'll be using is this equation of state. So du equal to TdS minus PdV. This is a very well known thing, um, and the analog, so this is analogous to du equal to dq minus dq plus dw. But of course this equation is wrong under many circumstances, and this is never wrong. This is an equation of state, while this is something related to the path, and so dq will change, dw will change, but these guys do not change no matter what path you take. Right, cool. So this is the main equation that we'll be using, and we'll also be using another really nice property of the thermodynamic systems, is that everything can be written in terms of two variables. So for example, you want to write energy for maybe a gas, and you can write it as just P times V, or maybe you want to write entropy for a gas or some other system, you can write it completely in terms of just like two variables, maybe like something like kbp, natural log of pv power gamma upon some, of course, constant thing. We don't know what that is, but yeah, so that is the whole idea. Actually, I shouldn't write it like that. I should write it as vt power f by 2 or something like that. But so that's like the idea that everything can be written in terms of two variables, and even like the pvt thing, they are related, right? You have an equation of state, which is kind of the basic requirements for you to say anything about a particular system, right? So for example, for gases it's just pv equal to nkbt, right, or something like that. Okay, right. So what we are basically saying is that all thermodynamic quantities are functions of two variables. Let's call these variables x and y. We won't specify what these variables are, but they are somehow related to these values. And so, well, basically you can say that pressure is sorry, I shouldn't say pressure, but more like, okay, so let's just say that x and y is so these are from this set of values s, p, v, t and e, right? For now let's just forget mu and n. Let's assume n is constant, so that mu doesn't even really come to the picture. But yeah, so let's just say that x and y are among these, and x is not equal to y. I mean, obviously, because otherwise everything would be an equation of one variable, which is kind of stupid. So in this particular case, given x and y, you can pretty much figure out all of these values, right? Because you know that every one of these can be written as any two of these, basically, right? So for example, if your x and y were p and v, then you could write entropy s in terms of p and v. You can write energy in terms of pv. You can write temperature as well, right? And yeah, because pv equal to nRT, so that stuff. Okay, so now we just use that fact and rewrite this equation. So we just have du equal to tds minus pdv, but we know what t is. So t is just partial mu upon partial s when everything else is constant, right? So yeah, so when you have everything else being constant, which is like your pressure is constant, your volume is constant, your, I think that was the thing. No, it was under constant volume that you would say this thing. Yeah, because du equal to tds minus all that stuff. Right. I suppose that's just the thing. So that's what temperature is. You know what, let's not do this. Let's not do this stuff, because temperature is already something that can be written in terms of x and y, so we don't need to do this. Okay, so now how do we make sense of this thing? Well, let's put a dx in the denominator, so you just get like du upon dx equal to tds upon dx minus pdv upon dx. So like over here what we essentially did is like we took the partial differentiation with respect to x at constant y, right? But you could have done the exact opposite, so you could have done this thing, right? Okay, cool. But how does this help us? Well, you can differentiate it again, and that is something that is going to in fact help us. right? So if you differentiate this with respect to y again, what you essentially get is this double derivative thing. And there's a nice property of double partial differentiation, that it's commutative. So like partial derivatives are commutative, and that could be used to do some really nice stuff. And so this just gives us, using the product rule, this gives us partial t by partial um, you know y, partial s by partial x, but plus t times partial s squared, sorry, partial squared s, right? That's the thing. Partial squared s by partial x partial y. I'm just writing it partial x partial y, not caring about the order, because you really should not care about the order. And we should also be writing this a bit smaller. Okay, yeah, some of that got erased. Anyway, so this is the idea. You will have these terms. I'm just gonna write things neatly because I kind of need that. All right, so that's the first two terms from this guy. Then you also need stuff from here, right? So you will have the same shenanigans. So you just have minus partial p by partial y, and then you just have partial v by partial x. But then you also have this plus, sorry, it's just it's actually a minus, right? Yeah, so minus p partial squared v upon partial xy. And similarly, you're gonna write this equation as well. And so what do you get? You just get partial squared over there, partial squared u upon partial x partial y, and that's equal to, so once again you do this stuff with this guy, so you just get partial t by partial, so now it's with respect to y, so now it's going to be with respect to x over there, so partial x, right? Right, and then you got partial s by partial y. Okay, plus, so the same stuff, p partial square s upon partial x partial y, not caring about the order of differentiation because we don't need to, minus this stuff, so just partial p by partial x, partial v by partial y, right? Minus p partial squared v upon partial x partial y. Now, why did I do all of this stuff? Notice that these terms, the double derivative terms, they are the same, obviously. So what we can do sort of is just subtract these two equations, and so what you will basically get is something like partial t upon partial y, partial s upon partial x, right? And then this term, so minus partial p by partial y, partial v by partial x, that's equal to so once again this term is gone, and well, this term is gone, this term is gone, so you just have these two remaining, so you just have partial t by partial x partial s by partial y. I'm gonna write it slightly smaller. Okay, and then you have this minus thing, so minus partial t by partial x and partial v by partial y, right? So this is kind of the equation that we really need. So I'm just gonna move it to the next page. And so now what we'll do is we'll just start plugging in values of xy over there, right? So we'll just do all sorts of different all the what it's like 5, so all the 5c2 ways that you could write this. Of course it wouldn't make a difference because it's symmetric, so I guess it's 5c2 upon 2 basically, so it's like just 5 things that you'll be having. And yeah, so let's just start putting in stuff basically. Oh, in fact, actually it's not even that, it's yeah, it's actually 5 variables, sorry. So it's like that's so 5c2 is just 5 times 4, it's like 10, so it's 5 actually, I guess. Yeah, that makes sense. So you'll get 5 equations from this. Okay, so let's just put x equal to s and y equal to p in that, and let's see what happens. So putting x equal to s, you have this term being just 1, then partial t by partial y. So now I just have, so once again just to write down x equal to s, y equal to p, right? Okay, so you just get partial t by partial p add a constant entropy, right? And that thing is 1 now. So minus partial p by partial y is once again just 1. So minus partial v by partial s at constant pressure, and that's equal to, once again you have this stuff. So so now it's just like it's changed, so it's just partial t by partial, what was it, this partial s at constant pressure minus partial v by partial p at constant entropy, because everything else is precisely the same, right? So let's have this partially partial x is entropy. Oh, that's not good. And y is pressure over there. Okay, this is slightly different. Yes, it is in fact slightly different. We'll have to change a few things. So this will be now what? This will be partial t by partial s at constant pressure, but that times of partial s by partial p at constant entropy, right? Cool. But then you can do one sort of trickery and say that, well, this thing is basically like 1 upon partial p by partial s at constant entropy. Wait, something is wrong. Obviously you cannot do this because at constant entropy it's 0, so this term just cancels. Something's messed up, isn't it? Oh, right. So because these are now changed, so these are like flipped, right? What that means is like both of these will just be 0 at this point, because everything is written in terms of s and p, right? So we just get this equation essentially, which is the same as saying you get this equation not equal to 0 now, right? And this is like one of the first what Maxwell relations. Okay, so that's s and p. So there is no point in doing p and s now because it's symmetric. So let's just go with s and y equal to, I don't know, v. Yeah, that looks cool. So let's see what we get. Also, I don't think we need to be doing the energy thing anymore. It's kind of not useful, right? Because you kind of used up the energy thing in the first place. So let's just use these and let's get some stuff. Okay, cool. So now what do you have? Yeah, so x is s and y is v. So now this thing gives us partial t by partial y is just partial by partial v, and now this thing is just gonna become 1 over there. And this thing just becomes 0, right? So you just get partial t by partial y, partial v at constant entropy. That's equal to, because this is now 0, right? Similarly, whenever you have partial s by partial v, now that's 0, so now you just have this term remaining. Now that's 1, and you got minus partial p. That's a negative, just beware of that. Minus partial p upon partial, so instead of x you have s now, and this is at constant y, which is constant v basically. Alright, so that's another equation. So 2 done, 3 more to go, because we know that we're gonna get 5 equations. No, wait, actually now we'll just get 4 equations, because 4c2 upon 2, so that's yeah. So wait, how many is that? So 4 times 3 upon 2 and that upon 2, so it's just like actually 3 equations, isn't that right? That's sad. Okay, no, we are in fact getting 4 something's wrong. So we got 4 of these guys and then 4 choose 2, that's 6. So 6 upon 2, why is that the case? Yeah, I mean, think about it. With s you have p v t, so that's already 3 equations, but then you also have p and v and p and t and v and t, so right, it should really just be 6. Obviously it's choosing, so when we choose there's no permutation thing, obviously, so we should actually be getting 6 equations anyway. Anyway, that just yeah, that was stupid. Anyway, so we will in fact be getting 6 equations. So 2 done, 4 to go. That's a lot, but let's go, let's see what we get. So now let's just put x is equal to s and y equal to t, right? And that's finally going to get rid of this s stuff now. Okay, and once we get rid of s stuff, we can also kind of do some really nice thing which I'm going to show you later. But first let's get this equation. So put x equal to s over there. This thing is 1, so just have partial t by partial t. Okay, that's problematic. What is that? That's just 1, isn't it? Okay, so just have 1, then minus partial p by partial y and partial p by partial x. So y is t, this thing is s. So minus partial p by partial s. No, t, right? And partial v by partial s, right? This is a constant entropy, constant temperature. Cool. And that's equal to, notice when I say constant entropy, I mean just that your entropy is constant. Everything else could be changing as you wish, but your entropy is constant. Fine. And that's equal to this stuff. So partial by partial x is now, okay, this term is gone because it's already having a 0. And then this stuff, so partial p, so negative partial p by partial s at constant temperature, partial v by partial t at constant entropy. Okay, amazing. That's negative and that's negative over there. I think that's okay. Fine. So that's another equation that we have. Wow, this is really complicated actually. So now you have 3 equations involving this s variable that you have. You can use these equations to do some really cool stuff. First, we'll just be using these 2 equations, and that's gonna give us, so essentially what we kind of want to do is just have a okay, this is sort of problematic. That's okay. Okay, let's just do this thing. Fine. So once you are under constant entropy, you just have to choose some other variable and everything just can be written in terms of that, right? So let's just start writing everything in terms of volume at constant entropy. So essentially we want to write temperature in terms of volume. So now t is a function of v, p is a function of p, right? Yeah. In that case, you can use the multivariable chain rule. Sorry, just the chain rule, and say that dt upon dp is equal to dp upon dv, and then I'm just writing it really bad, isn't that right? So dt upon, I should not be writing it like that. It should be v over there, right? So dt upon dp and then dp upon dv, right? So you can do this thing, and what does this give us? And this is all under constant entropy, right? So essentially what we're saying is take this under constant entropy, take this under constant entropy, this under constant entropy, right? Cool. And so far it's not all that complicated, like this is okay. But now what we can do is we can use these relations and then substitute those in there. And so what does this give us? It gives us partial v by partial s at constant pressure. That's what this term is now. And so you just get partial t by partial v constant entropy, that's just equal to partial v by partial s at constant pressure, and then this stuff, so partial p by partial v, which apparently is not there at constant entropy. Oh, but this thing is there certainly. So partial t by partial v at constant entropy is just this stuff, and so you can write that. So it's just minus partial p by partial s at constant volume, and that's partial p by partial v at constant entropy. And so that's relating pressure, volume, and entropy in this fashion basically. And this can also be written in a different way, because you can, at constant volume, both of these are just, right, at constant volume you can write pressure as a function of entropy, and then you can write this whole thing as the reciprocal and stuff. So what you essentially get is like partial p by partial v at constant entropy, and then partial v by partial s at constant pressure, and partial s by partial p at constant volume, that's equal to -1. And this is sometimes called like the what is it called? It's like circle rule or something. But yeah, that's the way it is done, right? So using the chain rule and then using these one of these relations. But notice what we essentially did. We eliminated this extra variable t, right? So this had, you know, this had basically like four variables involved in this equation. You had t, v, t, and then you had this entropy, because that's the condition, right? Under constant entropy. So you already have one equation of states that you need so that you can have this restriction, and then you can write this thing, right? So we sort of boiled it down to just these three variables, p, v, and s, and that's how we got this thing. Yeah, amazing. And we can do something similar for temperature as well. So then what you will need to do is, uh, you know, have a t over there, so under constant temperature everywhere, right? And we'll be able to do that once we have like once we know what happens for temperature. So let's just keep pushing on. So this will put to the side. Actually, I'll just put it to the next page, in fact, because who knows, you might need this. Anyway, so we're just gonna delete this thing. So you got the third equation. Let's go for the fourth one. So now we'll put x equal to something different, not entropy. So it's p, and y equal to v. Yeah, the usual PV thing that we use all the time. Um, okay, so let's do it. So what do you have? You just have partial t by partial y, which is partial v, under constant x, which is p, and that times of partial s by partial x, right? So notice this is like basically like tds minus pdv, so you can sort of relate it to that. And just the, yeah, so it just changed basically, sort of like you have y and x over there and y and x over there, but now you have x and y and x and y. That's sort of the only thing, so I can kind of memorize this thing. Anyway, so you just have partial t by partial v at constant pressure, and then partial s by partial x at constant y, right? So that thing, x is p, so partial p at constant y, so at constant volume, right? I also like notice that, we sort of saw that you will have this, what do we call this thing, this circular rule thing, right? So you can just use those circular rules and sort of simplify these equations more, but we'll do that later, not right now. Yeah, anyway, so you just got this thing. Okay, then minus of this stuff. So x is entropy and y is, sorry, x is pressure, y is volume. So this is obviously becoming 0 in that case, because now v is a function of p and v, and obviously, so okay, who am I kidding? V is a function of v only because it is v. So this thing just becomes 0. That's what I want to say. And now this becomes equal to what? So partial t by partial x, and partial s by partial y, right? So let's just write it down. Partial t by partial pressure under constant volume, and then partial entropy upon partial, what is it called? So instead of y, now I just have v under constant pressure, right? And then this stuff once again sort of cancels, because partial p by partial x is just 1, but then, oh, so that's actually not cancelling right away. It's minus 1 instead. And I'm showing it. So this minus 1, right? Okay, so far so good. So you have 4 equations, 2 more to go. Yes, it's tedious, but that is the way it is. So then you have y equal to t basically. Now we should like really just use of some space. So all of this is like with respect to entropy, then pressure, and now we'll next go to volume and all that. So anyway, x equal to p and y equal to t. What do you get? Put that in. So since y is t, this thing just becomes 1, and over here it will just become 0, right? Yeah. And over here, since x is p, this thing will become 1, but here it will become 0. So now you kind of just know how to do this thing. Partial s by partial p under constant pressure, sorry, under constant temperature, because yeah, that's what is there, is equal to, so this thing is gone, isn't it? Yeah. Right, so you just have this thing remaining, so it's just minus 1 times partial y minus partial v by partial t under constant entropy, sorry, constant pressure, that's what I want to write. Okay, so that's one equation left now. Okay, yes, it is tedious, I already said it. Okay, so finally we are going to, so how many are done? 5 are done, right? Okay, special volume is done. We'll go to pressure and temperature is done also. So like now we go to volume and temperature. So going to volume and temperature, um, so notice what terms are 0 now. So this thing would be just 1, right? And this thing would also just be 1, right? But this thing will be 0 and this thing will be 0. So now you just have this transposed over there. So essentially what you have is partial s by partial v is equal to, so that transposed over there just becomes partial p by partial t, and this is a constant temperature at constant volume, essentially. Amazing. So these are our equations. That's one cyclic rule that you have over there. I kind of wish that we can sort of simplify this whole thing, but I didn't have my hopes up. Yeah, although it would be nice if we could actually simplify this thing. So but we can sort of write it in a different way. We can write it as 1 equal to this thing, right? And over here as well you can write it as 1 equal to something. So I suppose that's not too bad. Okay, I need more space. So this is minus of that, by the way. So that was a minus 1 over there. This is moved, this is minus, but that's a 1, right? So 1 equal to this thing and 1 equal to that. Yeah, notice that these are kind of the reciprocals over there, isn't that right? Yeah, but the conditions are very much different. Okay, so these are our 6 equations, so the Maxwell's equations, right? Yeah. Can't we sort of simplify this stuff? I really need to simplify this thing. Okay, so first we can use this thing, partially by partial v under constant entropy thing, to sort of simplify this stuff. So it just becomes partial s by partial v under constant pressure, right? Yeah. That's under constant temperature. We don't like that. So you can use this thing basically. So we can sort of simplify everything using just like PV and S, I suppose. Right, so we'll just like try to eliminate one of the variables from here. So S is already predominantly being used, so we just need to delete this thing and delete that thing or something like that. Yes. Right. That is sort of useful. Okay, so there are like multiple different ways to be writing this. I don't think it's going to be simplified in any case, right? Okay, so that's pretty much it. That's how we get to these equations and how we do this stuff, and yeah, I guess. So every time you see this sort of stuff, all you have to do is like make these subscripts the same, and then it just comes down to being the chain rule. So yeah, that's pretty much it. So every cyclic equation that you will see, just make the subscripts the same, and then it's easy to derive that from the reverse. And so yeah, this is the Maxwell's relation. I guess I'll see you guys in the next video. Bye.